7 strategies for testing series. So in this section, we're going to get all kinds of series all put together, so we have to come up with a way of what's the plan of attack. Number 1, I always go with, if you can see right away looking at the function, the a sub n, that as n goes to infinity, that it doesn't equal 0, then that's the test for divergence. It's a divergent series. You're done. Number 2, I look at 3 easy recognizable formats: the p-series, the geometric, and the alternating series test. And you got your conditions right there and what you need to do. Okay. All right. 3. Now I line these up, the comparison test, I line them up underneath the p-series and the geometric series, because this is when we want to take, some crazy looking polynomial sequences top and bottom, or functions I should say, top and bottom, and break it down and compare it to a very simple p-series. But then you got to go through your direct comparison or your limit comparison, and the same thing with the geometric. Okay, your integral test. This is when you can see if you have to integrate it, it's going to be easy to integrate. A lot of times you're going to see 2 functions working here where a u sub will work great. So again, remember, it's got to be continuous, positive, and decreasing function. It's going to be an improper integral when we do our integral test. And so if our integral is convergent, then the series is convergent. If our integral is divergent, then the series is divergent. Also remember with the comparison test that if you have some negative terms that you can throw in the comparison test and make a test for absolute convergence first, because if that's true, then if it's going to converge absolutely, then it's going to converge no matter what. If that doesn't work, remember that little flow chart we made that you go to your alternating series test and then to see if it converges conditionally. Next, you have your ratio test and your root test. Ratio test, this is when you see a constant raised to the nth power. All right. When that happens, we want to use the ratio test. Here you see the entire function raised to the entire function raised to the nth power. Again, with the ratio test, really good with factorials. Remember, factorials will get bigger faster than your exponentials. Remember that in both tests, the setup is the same for their conditions. The limit is less than 1, they both absolutely converge. The limit's greater than 1, they both diverge. And if they're both limits are equal to 1, the tests are inclusive. All right, so next what we'll do is let's look at some of these and decide what we're going to do. So here, this is usually an in-class assignment where I get you to work in groups and talk about the process and what you want to do. So why don't you pause this for a second and then go ahead and try to work out these first 5 and try to decide what you want to do, and then go ahead and test for convergence or divergence. And let's not worry about having to show definitely everything's there unless we got to do some work to make something actually true. All right, so I'll pause the video and we'll look at the answers in a second. All right, well, welcome back. In the first one, first dead giveaway, raised to the nth power, raised to the nth power. So I would rewrite this whole thing, 2n plus 1 all over n squared to the nth power. Now again, you should put absolute value bars in here, but because all my terms are positive, there was no need to do that since n is starting at 1. If there was a minus sign up here, then yes, I'd put it in. All right, so we're looking at the root test. This is where we're going to take the nth root of the absolute value of our sequence function and take the limit of that. So the n's gone, and you can now see that bottom power is bigger than top power, so the limit is 0, which is less than 1. Therefore, our series absolutely is convergent. So it definitely converges. Second one, -1 to the n power giveaway, alternate series test. All right, Our a sub n is definitely greater than 0. I put in all positive n's. It's going to stay positive, so it's greater than 0. So that means we're going to take the limit. Again, we can see that bottom power is bigger than top power, so the limit's definitely going to 0. Then we'll put in the n plus 1 for all of our n's. Make sure that that sequence is less than this original sequence. Or I should say the a sub n without the -1 in there. Do a little cross multiplying, some simplifying. We get 0 is less than or equal to n squared plus n minus 2, which just, by the way, happens to factor. So you get n equals -2 and n is equal to 1. So as long as n is greater than or equal to 1, we are going to converge. Both statements are true. And we are starting at 1 with our series, so that's good. Example 3 looks like a p-series to me. All right, so this is going to diverge, but again, it's got to be a comparison. So I drop off the plus 1, so 1 over 2n, that's going to converge. It's part of the harmonic series, 1 over n. So we know it diverges, but then you have to do the verification. So if we did the limit test on this one, take the limit of the original a sub n and divide it by the 1 over 2n or multiply by its reciprocal 2n over 1, you get 2n over 2n plus 1, 2 over 2 leading coefficient ratio tells us we're going to 1, so that's greater than 0 and finite, so that verifies that it does diverge. Number 4, n squared e to the negative n to the third power, seeing two different functions here. I see a good old integral test right here because I'm going to let my u be the n to the third, or maybe negative n to the third, and I'll let my n squared be part of my du. So we swap it out for x's. The limit as t approaches infinity, integrated from 1 to t. So like we said, we'll let u equal negative x to the third. So that means I'll have negative 1/3 x squared dx for my du, so we have to factor out the negative 1/3. Well, if you integrate e to the u, that's just e to the u. We'll test it. Well, bring back your u, negative n to the third, or negative, in this case, negative x to the third. Puts that in the denominator. So now we put the t in for the x. So if we put in our limit as t goes to infinity for our first term, this is heading to 0. Here we have just 1 over e to the first. So negative 1/3 times negative 1 over e, positive 1 over 3e. So it converges. This one here, I see n to the power. So again, I'm thinking p series, n to the first, get rid of the plus 1. I see another n to the first, so that's n squared. So my power is 2. So that's going to be what I'm going to compare it to. So if if p is equal to 2, that's greater than 1, so it converges. Now we have to do, again, limit or direct, whichever you prefer. Limit usually always works. So 1 over n times the square root of n squared plus 1 times n squared. The n cancels with the n. So here, again, we're going to have 1. If you think about the plus 1 not being there, that's going to be 1n, so that's going to be approaching 1. Again, that's greater than 0, and it's finite. So therefore, it converges. All right, so let's try the same thing with 6 through 10. Again, hit the pause button, work them out yourself, and then we'll go over them. All right, welcome back. N is in the exponent position here, so I'm thinking a geometric series, all right, even though I've got sine of 2n up here. So I can see that this is possibly going to be 1 over 2, all that to the n power, so that's my r, which is less than 1, so I'm guessing this is going to converge. So I'm going to compare this with my comparison test to verify it. So I know that the absolute sine of 2n. Remember, this goes from -1 to 1, so I'm throwing absolute value bars on it. 1 over 2 to the n is less than or equal to 1. So this is going to bounce back and forth between -1 and 1. So putting absolute value bars, I only have to compare it to the 1. Now, what did I compare it to? 1 over 2 to the n, or 1/2 to the n power. So that, like I said, is 1, so I know it converges. So if we verify this now, this part right here, to prove that it's true, we cross multiply. 2 to the n times sine of 2n is less than or equal to 1 plus 2n. So think about what's happening here. This value, again, we said, varies between -1 and 1. So this is going to be -2, or -1 times 2 to the n, or 2 to the n, or something smaller and in between. This is my 2 to the n plus 1 more. It's always going to be bigger, so that's true. Here, again, another p series, n to powers, n to powers. So another comparison test. What are we going to compare it to? How about n squared over n cubed, or 1 over n? So p is 1. That means it diverges. So again, limit test or direct comparison test. These, I don't like to jump to the direct comparison test because you have to put in all those n plus 1s and do a lot of foiling, so I rather do limits. So n squared plus 1 over n cubed plus 1 divided by 1 over n, or multiplied by its reciprocal. That's going to give me n cubed plus n over n cubed plus 1. Well, n cubed, the limit, horizontal asymptote, 1. All right, there we go. 1's greater than 0. It's finite. It diverges. Number 8, -1 jumping out at me. Alternate series test. 1 over the square root of n minus 1. Yep, that's going to have a limit of 0. We'll put in the n plus 1 and see if it's less than or equal to a sub n. So I put in my n plus 1 here. Now it's not so bad because it's just one of them. All right, so cross multiply. The square root of n minus 1 less than or equal to the square root of n plus 1 minus 1. So adding 1 to both sides cancel those out. So we're left with the square root of n less than or equal to the square root of n plus 1. That's going to happen all the time. And this is for when n is greater than 1. So this converges. All right, down here, this one I would, because I have n to powers, I'm thinking about trying to create a p series here. So this is n to the 1/3, n to the 1/2 times n to the first. That's n to the 3/2. So get common denominators between 1/3 and a denominator of 2. That's going to be 6. So 2 6, 3/2 becomes 9 6. Divide like basis, subtract exponents, n to the 7 6. 7 6 is greater than 1. So that means we are going to converge. But now we have to do our comparison test, either limit or comparison. So this one I felt crazy. I went ahead and we did the direct comparison. So n to take the original and less than or equal to 1 over 7 6. Cross multiply. And n to the 9 6 cancels with n to the 9 6. So this is now a negative term. This is a positive n term, so it's always going to be greater, so that's going to be true. So that verifies that it converges. Here, because n is in the exponent, even though there's an n squared, I'm going to do the ratio test. So the limit as n approaches infinity of a sub n plus 1 over a sub n, so n plus 1 squared plus 1 over 5 to the n plus 1 times 5 to the n over n squared plus 1. Again, we don't divide by the fraction, multiply by its reciprocal. So some of the things, remember what we did here, we probably break this down, very smart. 5 to the n times 5 to the first, so we can cancel your 5 to the n's. So that 5 multiplies to the n squared plus 1. And then we FOIL this out, gives you n squared plus 2n plus 1 plus the extra 1 is 2, which doesn't matter. The powers are the same. Horizontal asymptote rule, leading coefficient is going to be your limit, which is 1/5, which is less than 1. So remember what it says. If I'm less than 1, then I converge absolutely. And so therefore the whole series converges. All right, 11, 12, and 13. Again, hit the pause button, work these out. Come back when you're done. All right, welcome back. This one, definite P series, even though you have e to the 1 over 2. But just think about what's happening to this as n gets bigger. This is getting smaller, so this is becoming a very small number here. All right, so we got a P series. So P is 2. So with 2, I'm thinking it's going to converge. But I'm going to compare it to e over n squared. I'm going to consider this as a 1. So to verify this with my comparison test, e to the 1 over the n over n squared less than or equal to e to the n squared. You can cancel these out, and you can see e is definitely going to be bigger than e to 1 over n again. This is going to be e at first, and then it's going to be e to the 1/2, e to the 1/3, e to the 1/4, and it's always going to be smaller than e to the first. So that verifies, and we converge. 12, again, -1, alternating series test. A sub n is greater than 0. Everything here is positive terms, no worries. Limit, well, it's n to the 1/2 over n to the first. So horizontal asymptote rule, if you think, top power smaller than bottom power. So yes, our limit's going to 0. So let's compare. Square root of n plus 1 over n plus 1 plus 5 less than or equal to square root of n over n plus 5. Cross multiply. Do some simplifying. N plus 5 to go inside the n plus 1, inside the radical. You got to square that binomial first to put it on the inside, then FOIL it. Same thing with n plus 6. You square it, put it inside of a square root, then you can multiply those together. And then we'll just start canceling and simplifying things away, or you can just square both sides and start canceling your terms. But this converges. Here we got the root test because of the factorial. I see that right away. So here, raise both to the nth power. So I'm going to take the nth root of the absolute value, which technically I don't need because n factorial will generate nothing but positive terms. N to the 4th even power will be positive. So n factorial or n to the 4th. Well, remember we said factorials get bigger faster than any exponential. Even if your base is changing, doesn't matter, it will get bigger. So this will be greater than 1. And so in the root test, if the limit's greater than 1, then it's going to diverge. Now, if you don't believe me that, oh, my base is always changing, it's going to get bigger. So here's what I did. I put in x factorial as y1. Here's x to the 4th for n to the 4th. And going down my table, and if you notice, by the time we get to 7, 7 to the 4th is smaller than 7 factorial. After that, the factorials always stay bigger, so it's your limit's going to infinity, so it's greater than 1. All right, so that ends our section notes for today. See you at the next one.